I get it. I'm not going to be pedantic on that.
Yeah. So yeah, like the way you're thinking about it is a reasonable way to think about it, but I suspect this analysis has already been done and already shown that those alternate explanations don't fit, unless there's some new law of physics we don't know, and in that case, you got to put that together before we're going to start taking, like, given that the laws we have explain just about everything very well, in order to bring in a new unknown law to explain it instead, that's a pretty high burden of proof you got there, because you need to have something that explains better than what we already have, and that's not easy.
You say
We
that
gotta talk
the
about-
laws... Hold on real fast. I'm almost done. I'll pass the mic. You say the laws of physics explain things very well, yet you have to make up 96% of the universe's matter and energy in order to make your model work. So I would completely and utterly disagree with you. Thanks.
Well, as we go further from Earth, we understand it less well. So the things in the solar system are very well understood. The things in distant galaxies are much less understood. So if you want to propose a new theory for distant galaxies, that's got a much lower burden of proof, because you're right. I mean, physicists don't like dark matter and dark energy. They basically say there's got to be something out there. We don't really know what it is. If you can explain what it is, like, hey, you'd probably win a Nobel for that.
Is our solar system in a galaxy?
Yes, but the thing is, so you're going to pass the mic, and this would be a fairly long-winded explanation. I can come back to it.
What's the thing you guys are talking about? What works really well? Would you need a new law to invent to explain?
Oh, just laws of physics in general. He was talking about the Eddington experiment, where light bending around the sun allegedly because of gravity, and I was basically saying that the alternate explanations like refraction had been tested and didn't really explain.
Oh, dude, check out. We got presentations on that. Check out Base Audits on YouTube. His presentation on gravitational lensing. There's only one set of data for like this entire phenomenon that claims to prove it being real, and it's from like the 1920s or 1930s. And
Yeah,
they
talking
had
about
30,
1919, that it's been tested a lot more since then. Like, there's way more examples.
They had 32 sets of photographic plates, and they threw out 28 of the 32 and kept the 4 that agreed with what they wanted, what they expected, and the 28 that didn't agree, they threw out.
If so, that would be pretty appalling. But like, my point is, it's been tested a lot more often since then. It isn't just like one code data from 1919. Like, there's a lot more to it than that.
Yeah, you should provide some examples, because the conditions in testing gravitational lensing around the solar limb of the sun are actually extremely difficult, and most of the work is either assumed or simulated. We're talking about actual physical measurements confirming the phenomenon as being a thing in the first place. That was done in, like I said, like the 20s or 30s. Can't remember exactly what year. It's been a minute since I reviewed it.
1919, if we're talking about the same thing. But there are a lot of other times. It's actually one of the ways they've found that they're pretty sure they've demonstrated that black holes exist, is the gravitational lensing created by those black holes.
You have to have a baseline, bro, right? Do you understand? Like, you have to have a baseline to say, okay, this phenomenon that we think is a thing is actually a thing, and we know it's a thing, but it works this much, we can quantify it. You have to have a baseline for that. You have to start with something local that's supposed to be of a known mass and known size, and then you use that to say, okay, this is a real phenomenon we can now predict, right? That the sun is the thing they have to use for that, because it's the only thing nearby us that would be large enough of all these known parameters in order to use. And yet, once again, the case in which they did that to the sun was like 90 years ago, and they threw out 28 of the 32 measurements because they didn't conform with their predictions.
Yeah, but again, like, this was not the last eclipse. This was not the last time people tested this. And I just threw a link in the chat where, like, gravitational lensing, where you can see images that can't be anything else. Like, they've done things where, one star will appear twice or something around a black hole, or a cluster of galaxies, whatever. but the light will come in from two different angles, and it will be the exact same spectra. It has to be the same thing behind it. So,
Yeah, there's
but
a
it's
lot of
coming
assumptions when you have things like the Einstein cross, right? Like you have an Einstein cross, they're like, oh, you have light bending in four directions around some anomalous body, and the light must be coming from this source behind it because we just assume that it is, and it must be like taking four different streams and making a cross around some dense neutron star or black hole in the middle. Dude, it's all
yeah.
is extremely highly assumptive. Like it's the
But
phenomenon that is claimed to be happening is being listed as proof of the phenomenon because the assumptions baked into it are listed as the evidence. Like,
okay. The thing you have to remember though is science, like proof, is a bit of an elusive concept in science. We're not talking about math here. What you get is we make the assumptions about what equations we can expect to work, and then we go test them. And so far, this has passed this test, has passed this test, passed this test. It hasn't failed any so far. That makes it fairly reliable. If you can come up with a better explanation, like if you've got a different way of looking at it that produces equal or better results, then that's a very interesting thing. And most scientists, not all, I mean, they're human, but most scientists will be like, oh, okay, let's see if we can make this work. But you can't just, oh, you made an assumption and tested it and then got good results, you monster. Like that's not how science is done. They have to make assumptions and test those assumptions. That is science.
Quick
Everything
question:
else,
is math science?
math is the language of science. Like English is not law, but laws are written in English.
So a conclusive empirical test doesn't prove things, but a language does?
No, in science, nothing is truly proven. It's just really well validated so far. It can always be disproven. I mean, Newton's math worked extremely well for centuries until we're like, it misses in this, and this situation. So they came up with a new theory that was very similar to Newton, except in extreme situations where it had differences, and those differences explained the world we saw better.
So
That
you
was
guys are
science.
saying you never actually know.
I mean, if you say you absolutely categorically know something, like there's no possibility of disproof, you're not really doing science, though.
Yeah, Yeah, no.
But
That's what I was just summarizing. What you said. You never actually know when you do
yeah,
science.
you
When
can,
you when in your version
you
of
can be
science.
like, yeah, you can be pretty dang sure, but you can't be like literally 100% sure.
Yeah, you never know. I know. I get
Yeah.
it.
So, yeah.
I don't agree, but I understand that you're saying you do science and then you don't know after. It's interesting.
Well, I mean, the way I think about evidence and like probability and such, if you're familiar with Bayes' theorem out of statistics, it's basically how a mathematical explanation for how evidence works. But nothing has 100% probability or 0% probability, because as soon as you say it's exactly 100% or exactly 0%, you've closed off the possibility of any further evidence. Literally nothing in the world could convince me that 1 plus 1 is 3, because that just doesn't make sense. Math allows for
but
100%.
you're
But
you're
like
talking
science,
about you're talking about the aspect of unfalsifiability, and yes, that's like an important part of science itself, and like everybody agrees. But like, I think that you're not maybe realizing the multiple layers of assumptiveness that are like baked into one another, like layered on top of one another, that you're using in your framework to validate these phenomenon. Like, dude already presented to you your model, like the mainstream model of gravity, is horribly, horribly flawed. They had to say over 95% of the entire universe is not there, but it has to be there or else we're wrong. So we're going to quantify our error by inventing an exotic magical substance known as dark matter and an exotic energy state known as dark energy, neither of which have ever been observed in, I don't know, 50 or 60 years, but they just have to exist. Otherwise, our math is wrong. So they
yeah,
quantified their error and called it a phenomenon, and then all the phenomenon that depend upon your conception of gravity, such as gravitational lensing, Einstein cross, the actual empirical evidence that established these things as being real, which is in this case one experiment done 90 years ago in which they cast out like 80-something% of the data sets.
A lot more than one experiment.
Like,
There's
take
so
that
much
as
more than
being
one.
confirmation.
Again, though, when you think about science as like it's not a literal proof, it is this is the best explanation we have. And when you actually look at the amount of experimentations, it's a lot more than just that one experiment. So much more. When you actually add all that up, it's like, okay, is this explanation literally perfect? Does it cover every situation in perfect detail? No. But it's very, very good at the things we have the easiest ability to check. And if it's wrong at a scale of, 12 billion years ago, 12 billion light years away, like that's not something we can stick in a laboratory and fix. It's a harder problem, and so our solution isn't as good. And yeah, that is a problem. Like most physicists, if you ask them, will say, no, I don't really love the concept of dark matter. Or, yeah, I think we figured out it's probably neutrinos. It's probably whatever.
Hey,
It'll
I
be
can
one of
perceive.
the.
Hold on, just real fast. I can perceive that you're not a anti-flat earther. Do you have a degree or specialize in something?
I was a chemical physics was my degree when I started university. I decided that I liked arguing politics more than doing homework, so I graduated with an economics degree. But I did get up to about third year in hard sciences.
Okay, please continue.
Well,
Sorry
let me
for
ask you this. Let me
And my
ask you
wife's
this.
nurse.
There's a tree. There's a tree in a car, right?
Yeah.
And they're smashed into each other, right? You were driving a car around all day. You went and did groceries, paid your electric bill, and then it hit the car, hit a tree, right?
Yeah.
Here's the question, physics question: did the tree move into the car, or did the car move into the tree?
That isn't really a meaningful question in the modern understanding of physics. You can look at no, I mean, in all seriousness, you can look at it either way. Now, in practice, we usually want to use a normal reference. You could use the reference frame of the windshield wiper, and the entire universe is going up, down, up, down, up, down when it's raining, and doesn't when it's clear day. Like that is a perfectly legitimate way to do physics. It's just really annoying and overcomplicated. So nobody does
So
it
you
that
don't.
way. But the
So you
laws of
don't know
physics.
which. So you don't know which one moved into the other one. All right. So,
Well,
but you're gonna.
okay, if you say you want to look at an inertial reference frame, you can do it. But like a model of the world where the car is always perfectly stationary and when the engine's running, the entire universe goes the other way. The laws of physics do actually work. It would be
All right, so
silly,
you don't.
but it's
Yeah,
possible.
no, I get it. I get it. So you don't know anything when you do science. You don't know
I
if how cars or trees work. I mean, what
no,
like
we know very
what are
well
we
how
gonna
they
do?
work.
What are we gonna do? You don't know how they work because you don't know which one moved into the other one.
Well, we know they
Hey,
moved into each other. Like under any frame of reference, they moved into each other, right?
yeah,
Yeah, but you
you
don't know
ever
which one was moving in towards
heard
the
of
other one. No.
Newton's bucket, bro?
Go ahead. Somebody was
Yeah,
roboting,
like
whoever that was.
absolute space has to be real.
We heard you,
I
Piezo.
asked
Go
him,
ahead.
have you ever heard of?
Jesus, your
Can you hear
robot.
me?
You're cutting in and out,
You're
Jesus.
cutting in and out pretty badly. I'm hearing parts, but I'm not hearing full
I just
sentences.
want to remind
You're
everybody earlier. Remember when I said I'm an expert
you're good
driver?
now,
That's why.
Piezo. Hold on, Larry. You're good now, Piezo.
Okay, you can hear me now. Yeah.
No, you're a
Uh,
little like.
uh,
You're breaking
I
down.
will be,
Yeah, you're robot, Piezo. Go ahead.
I'm just going to remind
never
everybody
mind, never
earlier.
mind. I'll wait.
Wait, you're coming through now. Try again.
Oh, okay. I was saying, have you ever heard of Newton's bucket? Because absolute space absolutely has to be an actual thing. Uh, Otherwise, you're left without a reasonable explanation for why the lab frame is the preferred frame in which in is the only frame in which invariant quantities can be reliably measured and predicted. You have a bucket. You spin the but you put an observer inside the bottom of the bucket, feet welded to the floor, You spin him, he sees the stars above his head spinning. You put that guy under the premise of relative motion doesn't know whether it's him and the bucket rotating or whether it's the world around him spinning and the stars above his head rotating. He can't know, right? Because they're kinematically equivalent. But then you put water inside the bucket, and he notices now as he looks up at the sky when he sees the sky spinning, he notices that the water is moving up the sides of the bucket. Now he knows absolutely that it is actually, in fact, himself that is moving because he has a centripetal force inside the bucket causing the water to ride up the walls. Therefore, he must be the one rotating. So as soon as you add that water into the system, you know that he's the one that's rotating. Now, with respect to what is he rotating? He has to be rotating with respect to some absolute background, because otherwise the only other explanation you would have is to say that he to say that the water is going up the sides of the bucket because the stars millions of light years away are spinning, which would be absolutely retarded.
If you do the math, this is going to be a very unsatisfying answer. I'll tell you that right now. But if you do the math, you can do it either way. And I agree okay, the inertial reference frame of the universe, the one where there are no, they call them fictitious forces, and ones where they are a result of the way you do the math is moving rather than inertia. Any non-inertial force, anything that doesn't follow Newton's first law. You can have reference frames that are inertial and follow Newton's first law. Or you can have reference frames that aren't. Newton's bucket basically is telling you what the inertial reference frames are, which is an important thing. Like it's a very useful thing to know.
Yeah,
But the
there's a
math does
preferred one,
work
bro,
either
because
way.
you have to have the lab frame. You have to have it because if you throw that bucket out in deep in the middle of nowhere in deep space with no anchor, you now have absolutely no way to know how to predict any kind of centrifugal force. You wouldn't predict any. You would predict zero. You would have no centrifugal Coriolis-Euler forces present out in deep space, right? If you don't have some inertial reference frame, you have to have one. That means that there must be a preferred frame. And
Okay,
not
if you
only
want to
this,
say
but
yes, sir.
real quick, not only this, he extends this idea beyond just the idea of the bucket. There's also Newton's coupled spheres, which paint the idea even more eloquently. He says you take two metal orbs, you attach a cable between them, and you pull it taut, so there's tension in the line, right?
Yeah.
But there's no tension, but like there's no slack in the line. You take all the slack out of the line, okay? You
Yeah.
cast these spheres off into deep space, okay? There's nothing else around them, okay? Now you have these spheres, and you look and you see them, and they're rotating, or from a certain reference point, they might be seen as rotating. Now you ask the question: is it the spheres that are rotating, or is it the world around them that are rotating? Right? Relative motion.
And gravity pulling them
The
together is the
answer is
explanation. Yeah,
no. The
no,
answer: if you measure tension in the cable, you know it's the spheres that are rotating because the tension in the cable is a product of their angular velocity, and there's no gravitational parameter involved in tension whatsoever. It
okay,
needs
slightly
not a
different
filter
from where I thought it
any
was going,
frame.
but that makes sense. Yeah, like that. That's actually a pretty elegant argument. I gotta say, I see where you're going with all this, and if your argument is just there is inertial and non-inertial reference frames, I agree. That is a true
No,
statement.
no, that's
Inertial
not,
frames are
no.
usually a lot more.
There's a universal absolute space, which is the ultimate inertial frame grid for the universe, with respect to which
Yeah,
all rotation can be measured, and things
yeah,
like
there
tension
is.
and spheres can be measured.
Yeah, no, there is one inertial reference frame in the universe, and that is definitely a more useful one than most others. Um, like in practice, just about the only inertial reference, or sorry, the only reference frames anyone's ever going to use are going to be the inertial reference frame, the Earth reference frame, and like the reference frame of a vehicle. Those are the only ones
But
anyone ever actually uses in
but,
practice,
but
right?
all the measurements made on Earth, treating the Earth as the lab frame, are congruent with this absolute space. Like they're equivalent, they're equal to one another. It demonstrates that that Earth is actually inertial.
No, they're not. Like, they are for a lot of practical purposes because the Earth's acceleration is fairly slow. But sorry, I'm pouring myself some water. But there are differences. Foucault's pendulum is the classic example. There are others, but there are non-inertial aspects to the Earth's reference frame, and those can be tested for most practical
Pendulum,
purposes. The Earth is good enough, but it's not literally inertial.
Foucault's pendulum and a ring laser gyro are explained the same way, right? The 15 degree per hour rotation or precession.
Yeah,
That's
that's
explainable
the Earth accelerator.
under that's explainable under a rotating ether, bro. That's what causes it. Because
Okay, but
you can
the
take
thing
things
is,
like Airy
you were the one
failure.
arguing that if you've got like the inertial reference frame and the privileged frame you've got, that all those Newton's bucket, Newton's mass, I can't remember what you called it, all those arguments show a single inertial frame for the universe, which is fine. But if the
Which is
ether
Earth.
is rotating, then the ether rotation is that inertial reference frame. The Earth, the quote unquote
No,
stationary Earth, would not be inertial in that context.
the ether rotates with respect to the Earth.
Okay, but like if masses are being accelerated, which is what Foucault's pendulum demonstrates, like that is the acceleration of a mass. It is
Yeah, there's
moving
a
in a different
differential.
direction than it was
There's a
before.
there's a differential pressure on the inner and outer surfaces of the pendulum body, which there's a differential velocity, but from the
But
ether
that's
field
not
that's
inertial.
rotating, the angular velocity of the ether at one edge versus the other edge is slightly greater, creating the differential in pressure that's causing the drift.
Okay, but again, that means it's not inertial, right?
No,
Like
the Earth is the thing that
there
it's
is an
rotating with respect to.
immaterial substance of the natural
Gotta go.
universe that causes pressure on things. That means it's not an inertial reference frame.
Yeah, I don't know how you know that. You don't even know if the pendulum's swinging or not. You don't even know if the pendulum's moving, right?
Well, okay, I
The
mean the
tree in the
inertial
car
elements.
thing.
Okay, the real world answer to the tree in the car thing is we're using the Earth's reference frame because we're not stupid, and therefore it's the tree is still in the car's moving. But the math works equally well either way. It's just one of them makes more sense.
Yeah, we went over the tree in the car one. You didn't know which one's actually moving in reality, but you're gonna
Well,
tell us the pendulum. You don't know if that's moving, right?
Well, okay. I mean, the answer is the same. You can construct the equations either way, and a non-moving pendulum in a moving universe, or a moving pendulum in a non-moving universe, the math is equivalent. But I'm not dumb. I'm going to look at the non-moving universe and the moving pendulum
But you don't
because
actually
that's
know though. So I mean,
uh, you
you
know.
know? You don't know. I don't know. What are we gonna do?
Well, we're going to be sensible people. We're going to use the one that makes sense.
I mean, I don't. I guess if you never know what's moving, though, how can we have conversations about moving things that are moving? There's no point really in it. I don't know. Maybe Piezo will find something out.
The same way we have a lot of other conversations. We have implicit context that we're assuming.
We're
Like,
not definitely not gonna be talking about science because that's when you don't know. You don't know anything after you do science. So
oh, you know quite a bit. Like that's the dynamics of the system because those are the same in either situation. It's like it's what label you put on it. It's the difference. Like potential energy. Pick something that is pretty similar through all systems. Gravitational potential energy, or whatever you want to call it if you're not a believer in gravity. You lift something up, you're putting energy into it. You let it fall down, you're taking energy out. What the zero line
did you
means
lift the thing though? Did you
is
lift it
completely
or did the ground
arbitrary.
move down?
Sorry?
Did you actually lift it or did the ground move down?
Let me finish my point. Sorry.
Okay.
Whether you say that zero is sea level, or zero is the top of Mount Everest, or zero is your head, or whatever, the 0 point is completely arbitrary. You can do the math either way. It doesn't matter which 0 point you use. You just have to do the math consistent. So if you say, what's the real 0 point for potential energy? Fuck if I know. It doesn't matter. What matters is the dynamics of the system. What matters is if I raise something up or drop it down, what does that do to the energy of the system? It doesn't matter what the baseline number you assume is.
Yeah, but we don't even know if you lifted the thing up or the ground moved down.
It doesn't matter. Like, it matters
And
for
then if
normal
this is anything to
conversation.
do with science,
In
if this is
normal
anything to do with
conversation,
science,
in normal
sorry, go ahead.
conversation, we're going to implicitly assume which one is the truth, because for normal real world practical purposes, there's an obvious answer.
Yeah, but
But the
we're here to
math work.
find the truth. We're here to find the truth, not assume it, though. If you can never know the truth, I mean, I don't.
But the truth is the
What are we?
same
What
either
are we
way.
going to get out of you?
I mean, okay, how much energy does it take to lift a dumbbell when you're at the gym? That's the same whether your 0 point for potential energy is sea level or the bottom of the deepest ocean or the top of the highest mountain. It's exactly the same. What you call zero doesn't affect it. So, like, what you call movement doesn't affect the dynamics of how things move. It just depends which one do you say is the stationary. Like that. It's not a physically meaningful question. There's no prediction of the actual effect anything has in the world that is different depending on which one you say is moving. It's a question of language. It's not a question of science. And
No,
language
it's
questions are
me.
important, but they're very different.
Well, we're trying to figure out the truth on what's stationary, what's moving. You know what I mean? If you just never know, then I don't know. I don't know what we can really do with that.
But you know how things move either way. You know what? If I playing a game of pool and I hit two balls into each other, it doesn't change the prediction of whether it's going to fall in the cup. Based on whether, is the table moving at a constant speed to the side or is it just stationary? Like, it's the same either way.
Yeah, but we're here to figure out the truth of things. Like, did the ball move, or did the whole pool table move near you? You know what I'm saying? Did the car move or did the tree move? We're trying
But
to
I
figure
mean,
out the truth about reality, not
yeah,
this
no, but
not
you
this
know, just
science
the
where you
reality.
don't know, or we don't know how trees and cars work kind of thing. Like, there's nothing. I
But there's
can't
a
do
lot.
anything with that, 'cause if you don't know any, like, if you don't know anything, I'm trying to know more things. So
But you know quite a lot. Like, okay, if the car and the tree run into each other at this speed, the car is going to get smashed up. And if they're into each other at that speed, it won't. That is a thing that is predictable in either system. Like, you can say, oh, well, if they do this, then the airbag is going to go off. Oh, if they do that, then the passengers are going to die. Like, these are predictions you make. It doesn't matter which of them's moving. Which of them's moving is a question of how you describe the system. It's not what the system is.
yeah, it does matter which one's moving. We're trying to, like I just said, we're trying to figure out the truth about reality, about which one is moving. I know which one's moving 100% because we know how cars work, and we know we're not in Lord of
Yeah,
the
I
Rings
know
and
what you're
trees,
doing too.
and we know we're not in Lord of the Rings
But,
and trees are. Please let me just finish my statement.
sorry.
Yeah, we know how cars work. We built them. We know how trees work. We're not in Lord of the Rings. We know in that scenario we can absolutely know which one moved into the other one.
And again, for practical purposes, I agree. Like, I'm not dumb. I know the trees don't tend to move.
No, not for practical purposes. 100%. We know the tree didn't move, and the car moved into the tree.
Yeah. Yeah, unless you're like a logging camp or something. Yeah.
Well, I mean, a minute ago. So now you agree? A minute ago, you said you didn't know.
You don't know in the
This is a
sense of,
very whimsical
like,
position you have. I feel like.
I guess there's a few different levels, and my answer depends on which level you're asking on. And I know that, again, I know that some of these answers are going to be very unsatisfying to you. But there's the level of, do the laws of physics work the same whether it's the tree moving or the car moving? Yes, they do. This can easily be demonstrated if you look at the math. But there's also the level of, if I'm writing an accident report for my insurance company, I'm going to say the tree moved into my car. No, like, that would be ridiculous. So the two are answering different questions. They're asking different questions, and you look at them differently. You got to be able to handle both if you want to do really in-depth discussion of these things. So this connection, and everyone just goes silent.
Yeah, I was thinking the same thing, but I guess they stopped talking. Can you hear me?
Hear you a bit. What was that?
Oh, someone asked if they lost connection. And
Oh yeah, okay, yeah, I hear you.